Hi everyone, how are you all? Just let me know if everything is fine. Audio, video, everything is fine. So is everything working at your end? Just let me know. Okay, so we will start now. Just confirm if audio, video, everything is fine at your end. Okay, so once you confirm, then we will start. Okay, great. Now in this session we will solve more questions regarding the AIMT2. So basically we have solved few of the questions. I mean Deepak sir has solved few of the questions from his part. Now we will be solving more questions, right? Okay, so let's just get started. Now this session, particularly in this session, I think I will be solving, let me just tell you, till question number 50. Okay, so I will be solving till question number 50 in this particular session. Then I will schedule one more. Okay, so we will be having multiple sessions because I think it will be too long if I just take one session. So we will be having multiple sessions to solve the remaining questions. Now in this particular session I will be solving till question number 50. Okay, so I think there was doubt in this particular question, so we will be solving this question and other questions whichever doubt in whichever question doubt you have. Okay, cool. So let's get started. Before that, let me just know that how was the AIMT2? So was the questions too challenging? Do you think the questions was too challenging in the AIMT2? Okay, so yes, I mean it might be the case that you might have thought that okay, some of the questions might be too challenging, but these were all the questions to make you learn something new, right? So if you solve these questions, if you analyze these questions, you will be definitely learning something new, and that was the main agenda to give you some creative questions. Okay, so for example, this question was extremely creative, I can say, right? I mean this question was really nice. This is a simple. Okay, once you understand the concept behind it, you will see that okay, this is simple question, but it was a creative question, I can say. Okay, creative question. Basically you can solve this question in less than 40 seconds once I explain how to do this. Okay, in less than 40 seconds or even yeah, 1 minute, you can say 1 minute. Okay, in less than 1 minute, in less than 1 minute to be very ideal number to solve this question. Okay, less than 1 minute will be like will be the perfect number to solve this question once you understand the concept behind it, once you understand what is the similarity between prims and dijkstra. See, we have taken one class in the record, in the basically in the like paid lectures, we have taken one class regarding prims and dijkstra similarity. Once you understand these things, okay, then this question was related to the same concept. Okay, I mean once you understand what is the prims and dijkstra similarity, then this question will be very straightforward after that. So we will be solving few questions with the tricks. I can say few questions with the tricks in the sense with the smart approach. Okay, trick doesn't mean that okay you just need to apply some formula, but with some smart approach and with complete analysis, obviously. Okay. Yes, so we will be, let's just solve these AIMT2 questions and then we will be having AIMT1 remaining question solution also. Okay, so let's just get started. Yes, so time management was the key. So someone is saying that time management was the key here. Yes, definitely. So let's just get started. Let's just solve this question. So this question was a nice question. This question was taken from Crows. Okay, so let's just solve this question. What this question is saying. Host A is sending a large file to the host B and assume that host B has a data has no data to send. Okay, so they are saying in the option A or the statement A, host A is sending to B and B doesn't have anything to send. Okay, B don't have anything to send. That is the question is saying. Now host B will not send acknowledgement to host A because host B cannot piggyback the acknowledgements. So what do you think? Is this statement true or false? Just let me know quickly. So they are saying that if host B doesn't have any data to send, can't host B even send the acknowledgements? Obviously this is obviously false, right? Why that is false? Can anyone tell me? This is false because host B can anyway send the acknowledgement. If it doesn't have the data to send, then anyway can the acknowledgement. Piggyback is something which is basically optimization technique in the sense that if you have data, then along with the data you can definitely send the acknowledgement, right? That is called piggyback. Okay, that is called piggyback ACK. Along with the data, if you send the acknowledgement, that is called piggyback ACK. But if you don't have the data at all, then you can directly send the acknowledgement. So that is why this is false, right? Host B cannot, because of this cannot, this is false. Okay, so I hope that is easy. Now let's just move to the next option. So in the statement B, right, in the statement B, what they are saying, the size of TCP receiver window never changes throughout the duration. So obviously this is also false. I mean, this is the standard congestion control protocol where B actually advertises its size, right? Every packet that B is sending, it says that, okay, this receiver window size, okay, receiver window size at my end is something like this, right? So this is definitely false. I think this is obvious option. So it should not require any more explanation, because this is the obvious thing to observe here. Okay. So now let's just see option or the statement C. Host A is sending a large file to host B over the TCP connection. The number of unacknowledgement bytes that host A cannot exceed the size of the advertised receiver window buffer. Okay, receiver buffer. Obviously, like, it cannot keep on sending, right? That is a part of the flow control. So that is the part of flow control. So that is true, right? It cannot keep on sending more than the buffer size. Okay, it cannot overflow it, because that is the part of flow control. So I think this is true. Okay, so that is why this question is easy one, and only C is true. So that is why D is the correct answer. Okay, now let's move to the next question. In this question, this matrix A is given. Now they are saying just find out the eigenvalues. Okay, so first of all, observe that this matrix is upper triangular matrix, right? Okay, so in the upper triangle matrix, if you do minus lambda, let's suppose something like this, upper triangle, lower triangle. So basically, the determinant of this will be lambda power 4 only. Okay, I mean, if you find out the determinant A minus lambda I determinant, it will be lambda power 4. It means if you put the determinant to be 0, then it will be lambda equal to 0 4 times. Is this understood to everyone? See, since this is upper triangular, right? So maybe I can just copy this matrix first and then tell you. See, this matrix is upper triangular. So you don't have to find out the eigenvalues by doing the A minus lambda I. First of all, you don't have to do this. Okay, you don't have to do this. But still, if you do it, I'm telling you, still if you do it, minus lambda, okay, then it will be the determinant of this. It will be lambda power 4 only, right? Which is 0. So lambda is 0, 0, 0, 0. Is this okay to everyone? Let me know if there is any doubt in understanding this part, right? Now what they are saying, that lambda equal to 0 has algebraic multiplicity. Algebraic multiplicity means that how many times it is repeating. Okay, so it is 4 times repeating, then that is definitely 4. So either A is answer or B is answer. Now they're asking that what is the geometric multiplicity? Geometric multiplicity means regarding the lambda equal to 0. Geometric multiplicity means the number of linearly independent vectors, or in other words, if you remember, it is also called nullity. If it is lambda equal to 0, it is also called nullity. So can you tell me what is the nullity? Can you tell me what is the nullity? Nullity is basically rank minus, I mean, n minus rank, number of columns minus rank. Okay, so what is the rank here? Can you tell me rank? Since two linearly independent columns, so rank is 2. So nullity is also 2. Okay, nullity is 2. Since nullity is 2, that is why you can say that geometric multiplicity or the linearly independent vectors corresponding to lambda equal to 0 is also 2. So hence B is the correct answer. Okay, so this is the way to approach this question. This was really a nice question. Okay, it was involving multiple concepts, to be honest. Okay, I could have given this question in 2 mark. Actually, initially I was thinking to give this question in 2 mark, but then I thought that, okay, since it might not take much time, and I mean, sometimes it happens that I think, or like I or Deepak think that, okay, this question should be 1 mark, but we give it in 2 mark, or vice versa also. Okay, so it was a dilemma for me for this question, should I put it in 1 mark or 2 mark, but ultimately I ended up putting in 1 mark. Okay, it was a little dilemma for me, to be honest, when I was just deciding the marking for this question. Okay, yeah, that key, I think in the question paper I just marked by mistake, maybe the typo was happened, so C was the key, but we have corrected it, so now B is the key. Okay, so let's discuss all the questions. Is this question understood? See, it is involving multiple concepts. One concept is that first you find out lambda power 4 equal to 0, or maybe you can directly say, since it is upper triangular, that is why lambda equal to 0 will be repeating 4 times, right? This was the first concept. So that is why you can say algebraic multiplicity is at least 4. I mean, it is exactly equal to 4, not at least. I mean, you have found out the algebraic multiplicity, which is 4. Now, to find out the geometric multiplicity, you can go with this nullity way. Okay. Nullity is nothing but rank and number of columns minus rank. So these are the two columns. So nullity is 2. Right? It means geometric multiplicity is 2. So that is why B is the correct answer. So that is really a nice question. Okay. So others is saying that I could not solve this question because I was not able to recall what was the this geometric and algebraic multiplicity means. Okay, so yes, it happens. Basically, geometric. Let me just revise it. Algebraic multiplicity means how many times it is repeating. Geometric multiplicity means that how many linearly independent vectors you have. Okay, corresponding to it. Okay. Yeah, again, this was again a nice question, I can say, right? This was really a nice question. How many of you were able to solve this question? How many of you were able to solve this question? See, what this question is saying, that you have a pointer, but in this case you have a double pointer, which is itself a void pointer. Okay, so which means, what is a double pointer? There is a pointer, right, which is pointing to something, and which is pointing to something, right? Which is pointing to something, right? This is generally called double pointer. Now in this case, first let me know what is the void pointer, okay, and then we will solve this question afterwards. What is a void pointer, and why do we even need the void pointer? Yeah. So the void pointer is basically something which is very useful if you don't know the pointer type. Okay, maybe let's just define a void pointer. Void star p equal to, let's suppose void star p, right? Now what you can do, you can assign any address to this. Okay, but before assigning any address, okay, I mean, first you can assign any address, that's not a problem. For example, let's suppose there is any character c, okay, equal to, let's suppose, a. So you can do one thing, you can definitely say p equal to address of c. That's perfectly valid. I mean, you have actually assigned the address of c, which is a character. That's a valid thing to do. Maybe you can do with this the same thing with the integer also. For example, you can do void star p, okay, int I equal to 5 and p equal to address of I. Okay, this is also valid thing. Now once you dereference this, okay, when you want to dereference this, you can't directly do this. Okay, this is wrong. This is wrong because you don't know the type of this p, right? I mean, what kind of address it is storing. You can hold any kind of address, but you cannot directly do like this. So basically, since it is wrong, so what is the correct way? The correct way is that you have to first typecast it. So this is the typecasting. Okay, this is called pointer typecasting, and then you have to dereference it. This is the correct way. Similarly, here also the correct way will be int star p and then this is the correct way. Now remember that this is not the correct way. Okay, in fact, it is not making even any sense if you do something like this. This is again a wrong way. Okay, this is again a wrong way. Why that is the case? Because here in this you are dereferencing directly, which is obviously not allowed, right? This is not allowed. This is not allowed. Okay, so so now let's just do this question. Okay, what they are saying. Okay, before that, maybe I can just quickly tell you about the double pointers also. Suppose you have a pointer. Let's suppose you have a double pointer. Okay, int star p. What does this mean? It means that p is pointing to something which is pointing to an integer, maybe 5. Okay, p is pointing to something which is pointing to integer. Generally these double pointers, okay, I mean, you can use in this way, but generally these double pointers we use for the case of, let's suppose, we have some array or something like this, array of integer pointers. Suppose, for example, let me just give you the quick example. Suppose this is an array which is, each of this is pointer. Okay, this is the array of pointers. Suppose this is pointing to maybe 5. Suppose this is pointing to, let's suppose, 12. Suppose this is pointing to, let's suppose, -3. Suppose this is pointing to, let's suppose, 9. Something like this, right? These are the different numbers. Okay, 900, let's suppose. Now I want to point to one of this element. Okay, let's suppose I want to point to one of this element. Since it is a pointer by itself, so I can use p here because p is a double pointer. Okay, I can use p here and I can say p is pointing to this. P is not pointing to the whole array. Okay, so there's a lot of concepts here. P is not pointing to the whole array. P is just pointing to the one of the element of the array. Okay, P is not a pointer to array. P is a pointer to integer pointer. So now if you want to access this 5, what will you do? You will do star p. Star p will lead you here, and then once you put one more star, you will be going here. Okay, now suppose you do this value is basically 5. Okay, now let me just ask you a different question quickly. Maybe you know all of this, maybe you don't know, so that is fine, because it might be possible some of the people here may not know, may not, or maybe they have forgotten these things. So let me quickly ask you 2-3 things and then we will solve that question. Okay, so suppose I just ask you, what is this value? Star p. Okay, and then plus 1 star. Can you tell me quickly what is this value? Let me know. Yes, so this value will be, how much it will be? It will be 12. Why? Because star p means you are here. Now you are doing plus 1. It is like you are basically, this is the element of the array, right? You are here means this is the star p is the element of the array. Plus means plus 1 means you are going to the next element. I mean, see, sorry, I think it should be p plus 1, not star p plus 1. This should be p plus 1 and then star star. Okay, so p plus 1 means p is pointing here, p plus 1 will point here, right? And then star means you are here, and then one more star means you are talking about 12. Okay, so it will be p plus 1 star star. Okay, so it will be 12. Okay, is this fine to everyone? Let me know. Okay, so I mean, there could be multiple questions here. Star p, if you let's suppose have, you know, some element stored here, let's suppose 6. Okay, and if I just ask you star p plus 1 and then star, then what it will be? See, star p means you are here, right? I mean, you are pointing to this, and then plus 1 means this, and then star, then one more star means you are talking about 6. Okay, then in this case it will be 6. Okay, anyway, so basically what I'm saying, that if it is a double pointer, generally, okay, generally they points to I mean, they are useful for the array basically. Okay, I mean, it is pointing to one of the element of the array, an array of the pointers generally. Okay, but yeah, that's not 100% true, in the sense that you may not be having the following elements. Okay, you may be just pointing to one of the element. Okay, it might not be even array. Okay, I'm just saying that generally they use it for the array. Now let's just solve that question. In that question, what they are saying, let's just see. So they are saying that you have a double pointer which is a void type. Okay, so by the way, it is, you know, more of to confuse you for the double pointer for the void type. So let me tell you what it will do. So suppose you have p, right? So ideally p should be pointing to something, right? And which will be pointing to something. Now p is pointing to what type you don't know, and it will be pointing to what type you don't know. I mean, since it is everything is void, you don't know, right? You don't know that p is pointing to what type. But one thing is sure, that p is pointing to something which is a pointer itself, right? This is a pointer itself. That is for sure. But is it a character pointer? It is a integer pointer, in the sense it is pointing to ultimately an integer, or character doesn't I mean, you don't care, or you don't know maybe. Okay, but this is a pointer itself, which means p is pointing to a pointer. That is the whole crux here. Okay, so p is pointing to a pointer. So just see this, something like this. Okay, so it is star star p means p is pointing to the pointer. This is the whole crux here. So p is a pointer to pointer, or maybe let me write like this: p is pointing to a pointer itself. So now what will happen if you do star p? Oh, sorry, you are not doing star p. If you do plus 1, p plus 1, generally, as I told you, generally, I mean, they use it for the array, but it doesn't matter. Okay, so suppose, okay, hypothetically I'm asking you, suppose this is an array. Okay, now if you do p plus 1, so p plus 1 will be pointing here. Is this okay to everyone or not? P plus 1 will be pointing here. Let me know. Is this fine? P plus 1, right? So if p plus 1 is pointing here, p plus 1 is pointing here in the sense that this is a pointer. Let's suppose this pointer size, actually it is given in the question that pointer size is 8 and integer size is 4. Okay, pointer size is 8 and integer size is 4. So it means if this is, let's suppose if this is 1000, if this is 1000, now which means at 1000 it is stored, but it will be storing how many bytes? Can you tell me? It will be storing how many bytes? Okay, it will be storing how many bytes? Can you tell me? It will be storing 8 bytes. See, the thing here is that P is storing 8 bytes. Okay, P is stored because it is holding, let's suppose 1000. Okay, which will be pointing to some pointer. It is also a pointer which is pointing to something, right? Now this pointer of what type it is not known to you, which is fine. Okay, I mean it is pointing to character, it is pointing to integer, it is pointing to, I mean it may be a pointer to hold together array, it may be a pointer to 2D array itself. Okay, it may be a pointer to anything, it may be a pointer to whole word. Okay, you don't know, but it is a pointer, right? It is a pointer, that is what you know. Now if this is 1000, it means it is basically at the 1000, which is fine. Now can you tell me that whatever it is holding, what that thing be? It will be holding an address. Is this fine to everyone or not? It will be holding an address. I mean, whatever it you actually don't know that exactly it is pointing to what kind of data type, but it will be holding some address, right? That is for sure. Now, since the address size is 8 bytes, okay, maybe it is holding, let's suppose this is 5000 or maybe whatever, right? Let's suppose 5000. Okay, maybe it is holding 5000. Okay, but it will be storing the 5000 into 8 bytes. Even though we can store in less bytes, but it doesn't matter. I mean, it will be appending zeros because address is of 8 bytes. So it will be storing 5000 into 8 bytes. Is this fine? Is this fine? Let me know. So it will be basically storing 5000 into 8 bytes, which means what? Okay, which means what? That the next, if this is at the location 1000, okay, then the next thing, whatever is the next thing could be anything, but it will be basically starting at the, since it is taking 8 bytes, so the next thing will be at 1008. Is this fine to everyone? Right, the next thing will be at 1008. Now the thing here is that if you do p, okay, if you ask me what is the value of p, actually p is storing 1000, right? But p plus 1 is actually, if you ask me numerical value of p plus 1, it will be 1008, right? Now p plus 1 could be storing some pointer itself, like generally this is an array of pointers. Okay, it could be also storing some pointer, which is basically fine, right? But p plus 1 is 1008. Okay, I mean whatever p plus 1 is having, maybe it is not having the pointer, it is having integer or whatever, right? I mean I don't even know actually what this p plus 1 is having, I mean as a data. Okay, it is holding the pointer, it is holding integer, it is holding character, it is holding what it is holding, I don't know, but numerical value of p plus 1 should be 1008. Is this fine to everyone or not? This is fine, right? Now don't worry, I will repeat if there is any doubt. Now they are asking in the question, they are saying, okay, once you do p plus 1, then you typecast it to be integer address. So they are saying, once you do p plus 1, then you typecast this p plus 1 and you say it is an integer pointer. Typecast means you tell the compiler, okay, that what kind of thing that is being stored here, okay, how to interpret this. So basically they are saying that this 1008 is nothing but an integer pointer. I mean this is basically this location, okay, this location is storing an integer pointer. I mean it could have stored an integer by itself, okay, but they are saying that it is storing an integer pointer. So again it is storing something 8 bytes, okay, I mean it doesn't matter, but yeah, it is pointing to something. Okay, it is actually integer pointer, it is pointing to something. Let's suppose this is 5 or maybe 7, it could be, let's suppose 13. Okay, it is pointing to 13. It could have been stored at 6000 address, so it is storing 6000. Okay, by the way, I don't want to flood with so many numbers, so let's not worry about this number. Okay, so but yeah, it is pointing to some 13, okay, some integer, because this is the way we are interpreting it. Okay. Now what they are saying next? Okay. Now they are saying that you do -1 here. Okay. Now this is an integer. Okay. So basically p plus 1, yeah, p plus 1 will be 1008. Now you treat this as an integer pointer, right? So basically now you are doing -1. And what is the size of integer which is given to us? So let me just copy this. Okay, so size of integer is given to us as 4. Now how will this help? Let me just tell you. See, so probably let's just quickly do this again so that you will get to understand this more. So p is some pointer, right, which is pointing to something. Let's suppose p is holding, inside this p is holding 1000, which means this is 1000, right? Now here at this moment, this could be a pointer itself. Okay, this is a pointer itself which is pointing to something. Let's suppose whatever it is pointing to, okay, it will actually hold 8 bytes of address, right? It will actually hold the 8 bytes of address. So the next thing, p plus 1 will be here, right? So which means p plus 1 is numerically 1008. Let me know till this point if everything is fine or there is any issue. So p plus 1 will be 1008, right? Let me know if there is any issue here. Now if you're treating, okay, if you're treating this as integer pointer, so suppose, let me just ask you one thing. Suppose there is an integer pointer, right? Okay, let's suppose there is some integer pointer, maybe let's just call it t. Okay, int star t, okay, which is pointing to some array. Okay, I mean it could point to anything. Let's suppose, okay, this is pointing to an array, something like this. Suppose at this moment it is pointing to, let's suppose, this element of the array. This is having 1 2 3 4. Now if you do t minus 1, if t is pointing to 3, then t minus 1 will be pointing to what? T minus 1 will be pointing to what? If t is pointing to 3, it will be pointing to 2, isn't it? Tell me, is this okay to know to you or not? So basically, since the size of let's suppose this is, let's suppose this is 5000 or 6000, anything. Okay, let's suppose this is 5000. Then since the size of integer is 4, so it will be 5004. This will be 5008, and so on, right? So if I do t, if t is 5008, right, then t minus 1 will be 5004, right? So basically t minus 1 is pointing here, right? If it is integer pointer, if I'm treating this 5008 as an integer pointer, then -1 will do what? It will subtract 4. So if I treat this as a, I mean, since p plus 1 is there, so p plus 1 will give you 1008 numerically, right? Now if you treat this as an integer or integer pointer, okay, so you are saying that, okay, this is pointing to some integer. I mean, you are basically saying now this p plus 1 is the integer pointer, right? Now if you're treating this as an integer pointer, then then -1 will give you the integer before it, right? So which means if this is 1008, so basically this value will be how much? If you are asking, if you're treating this as an integer pointer, this will be 1004, right? So because the size of integer is 4, so 1008, see, if it is pointing to here, then t minus 1 will give you something which is 4 bytes back. Okay, so if this is 1008, then it will give you 1004. Let me know if that is okay to everyone or not. So maybe okay. So this 1000 should be inside, I think, right? Okay. So I think just let me tell you one more thing here. See, P is this. So it is basically saying that P is pointing to something. Now P plus 1 will definitely point to this. Is this first of all clear? Now if you're treating this thing as an integer pointer, then which means it is pointing to some integer, right? It is pointing to some integer. Now it P minus 1, or after typecasting it, it will point to the integer before it, right? So Q will be finally 1004. And you can also do this using the pointer arithmetic. That is the answer is available on the gate overflow. I mean, using the pointer arithmetic also you can solve this question. Okay, now let's just do the next question. This similar kind of question has been asked in gate, I don't remember the year, I think 2023, right? The similar kind of question we have also challenged that question, I think. So there was some mistake in that question, as per us. So but yeah, but I think the challenge was not accepted, but that is fine. So the similar kind of question has been asked in gate 2023, I think. So now in this question what they are saying, they want to have the aggregation, right? They want to aggregate these networks. Now they are saying that which of the CIDR notation can we collectively use to correctly aggregate all these subnetworks. Okay, so see, these four networks can be I have the binary here, so these four networks can be written like this, right? Now if you notice that, okay, if you notice this network and this network, right? So this one and this one is common, so maybe you can aggregate. I mean, to aggregate you have to have everything. I mean, you have to take all the networks which are having the common suffix, you can say, right? So for example, this network, right, this network and this network are basically having common till this point, right? Till this one. Okay, till this one they are having common. Is this fine? So you can definitely, let me just call it network number 1. This is 2, this is 3, this is 4. So you can merge 2 and 4, and similarly you can merge 1 and 3, because 1 and 3 is also having this till this point common, right? So if you merge, let's suppose this is a merging, this is 0, this is 1, right? Okay, if it is, so these two are merging, right? So basically if you merge these two, let's suppose 2 and 4, then you will say that, okay, till this one everything is common. So you can say instead of slash 24 it will be slash 23. I mean, after merging these two it will be slash 23, right? Instead of slash 24. Similarly if you merge 1 and 3, okay, if you merge 1 and 3, because till this 0 it is common, then you can say it is basically slash 23, right? Now you will be having these two networks. Now can you merge these two networks again, and can you make this as slash 22? That was the question. So the answer is that if you do this, right, it will be actually having, that cannot be aggregated into this, because it will be actually covering more IPs, and we cannot cover more IPs. Okay, so that is what is given in the question, that no, we are not allowed to include any extra IP addresses. Okay, so that is why final answer is this: we cannot merge these two. If we merge these two, it will be covering more IP addresses, right? So as you can see here, they could be aggregated into this, but this aggregation would include four networks that were not part of the original allocation. Hence the smallest aggregation possible is basically slash 23 only. Okay, okay, so let me know if that is okay. Okay, so 2 and 4 will not be merged. Okay, so you are saying that Which one you are saying it will be merged? So till whatever it is common, you can merge those, right? So let's just check it. I think till this point, it is common, right? Yeah, you can merge 1 and 2. You can merge 1 and 2 because till this point this is common, and you can merge 3 and 4 later words. Yes, till this point it is common. So you can merge 1 and 2. Sorry, I was just merging 2 and 4. There was some confusion in the binary, but yes, you can merge 1 and 2 because till this point it is common, and then you can merge 2 and 3. Okay, if you merge 1 and 2, it will be the answer. If you merge 3 and 4, it will be the answer. Yes, that is correct. Thank you, Siddharth. So Siddharth has told me that yes, you aggregated wrong, but now I think that is correct, right? Okay. Now suppose if we merge all of these four networks, okay. So suppose if you try to merge all of these four networks, so I think for all of these four networks we can merge because till this point only the things are common, right? Now we need to merge. This is 8, 9, 10, 11, right? So it will be slash 22. 8. So or it will be slash 21. It will be slash 21. It will be slash 21. If we merge till this point, it will be slash 21. But the slash 21, if we merge all of these four, right, it will be slash 21. But the slash 21 will be covering many more IP addresses. Okay, this will be covering many more IP addresses. Okay, you can even check that how many it will be covering. Okay, this is basically since you have 11, it will be 2 power 11 addresses. But these all together combinedly are not 2 power 11 addresses, right? How many addresses are these? This is 2 power 8, right? This is 2 power 8 addresses. So 2 power 8 into 4, right, which is 2 power 10 addresses. So these are 2 power 10 addresses, but if you merge all of this will be 2 power 11 addresses, which is wrong, which will be wrong, right? Okay, now let's see this question. There was some confusion in this question. Let's see what they are saying in this particular question. So they are saying, suppose the three processes exist in the ready queue, okay, ready state of the system as described below. Suppose the system uses primitive round robin scheduling, and T11 is running when the quantum expires. So currently T11 is running, right, which is fine. Now they are saying that these threads are implemented entirely at the user level with no support from the operating system. Which thread might possibly execute at the beginning of next quantum? Okay, so what they are saying that if you are having this kind of processes, and where each process is having some threads, but these threads are user level threads. Okay, so what does user level mean? User level basically mean that for these two threads system is unknown. I mean system doesn't know whether these two threads are there. So let's suppose this is CPU and you are scheduling P1 on the CPU. Then with this P1, is T11 is getting scheduled, okay, or T12 is getting scheduled? This is up to user. This decision is up to user. I mean system doesn't even know. So this is done by user scheduler. I mean there are libraries. Using those libraries you can use the user scheduler. Okay, so if you schedule P1, then according to system or according to operating systems, P1 is scheduled. Now in this P1, whether T11 is scheduled or T12 is scheduled, this is basically done by the user. Okay, you don't have any I mean the operating system doesn't have anything to say here because all the threads are user threads. Now since its time quanta is expired for P1, since I mean T11 was running, which means the P1 is now expired. Now can you run T12? See, for the operating system, it is just one process. Okay, operating system doesn't even know whether this T11 or T12 was running. So T12 cannot be run now. Why? Because operating system will either schedule P2 or P3. It cannot schedule inter process things, right? It cannot schedule within the process. It cannot schedule one of the thread. Okay, round robin at this level, not at the thread level. So P2 or P3 will be scheduled. P2 or P3 will be scheduled. Right now Now P2 is having these two, P3 is having just one. Now in this P2, which one will be scheduled? This is up to user. Okay, so maybe this is scheduled, maybe this is scheduled. So basically these three threads are possible to schedule now, right? So basically two, whatever is starting with 2 and whatever is starting with 3. Okay, so what if it is starting with 1, then it is not possible to schedule. This is not possible to schedule because operating system will either schedule P2 or P3. Is this fine to everyone? Okay, great. Now let's move to the next question. Yeah, this question was a nice question. This, I will say, this was an easy question only, right? And this was also, the earlier question was also easy, but yeah, it was little interesting question. So now let's just see this question. What they are saying, that if this is having the largest, it is booked. Second largest in the roots child, right child basically, this is also booked. Where will the fourth largest, right? So if you have to put the fourth largest, then basically since all elements are distinct, so you cannot put the fourth largest somewhere here. Why? Because see, for the fourth largest, you just have, I mean, third largest with you, right? I mean, that you can put. Basically, if you put the fourth largest here, then there has to be two more elements that has to be put here, right? I mean, you have to fill in the see, this is the largest, let's suppose 100, right? And the fourth largest, let's suppose 50 or maybe 80 or 190, let's suppose 90, 80, and then this is 70. Okay, so let's suppose this is the fourth largest. Now can you put the 70 here? Sorry, 100, 70. See, 90 is already there, 90 is already there, so you have just with you 70 and 80. I mean, if you have the fourth largest to put, you have 80 with you, which is the third largest. Can you put 70 here? The answer is no, because then 80 can either take this or this, right? You cannot implement in the decreasing order. I mean, you have to have the decreasing order here, right? But so you cannot have the decreasing order. So basically 70 can be here only. I mean, it cannot be in any of this leaf, right? 70 can be here, can be here, can be here. I mean, you can put it anywhere. The reason is that remaining 80 can be here, right? I mean, don't worry about the 80. 80 can be here also. So 70 can be here, 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 or here. Can the 70 be here? Yes, 80 can adjust here also, right? 70 can be here. Can the 70 be here? Can the 70 be here? Tell me. Can the 70 be here? Yes, right? Why? If 70 is here, 80 just at this place 80 can come, right? So 70 can be here, here also. So there are like many positions where 70 can be. Apart from these four, so 1, 2, 3, 4, 5, 6, 7, right? At 7 position, fourth largest could be there. Okay, if it is kernel level, if in this case, if it is a kernel level threads, then kernel can schedule any of this. For the kernel, all of these are independent threads, right? Then kernel can schedule all of this. Okay, I mean any of this. If it is kernel level thread, then all of this will be answer. Okay, if this, since these are user level threads and kernel is completely unknown, so that is why T12 can never be the answer here. Okay, so 7 is the answer for the fourth largest. It was also easy question. I mean, little tricky but easy. Okay, you can expect, okay, you can expect gate to ask these kind of questions. Gate definitely ask these kind of questions. I mean, we are not we cannot predict, and we should never prepare in this way, like, okay, will get asked this kind of questions or not, or something like this, right? So because otherwise your preparation will not be having the good shape. I mean, you will be keep on worrying whether gate will be asking this kind of questions or not. So don't sorry, you can X. So don't worry whether gate will be asking these kind of questions or not, but I'm just telling you that gate typically asks these kind of nice tricky questions. Okay, I can say cute questions in just 1 mark. Okay, in 1 mark they get generally ask these kind of questions where a student likely to do silly mistakes for these four positions. I think some of you have done it, right? How many of you done this silly mistakes and mark 11? How many of you mark 11? Some of you might have done it, right? Okay, now let's solve this question. In this question, what they are saying, that you are having LR1 DFA. Okay, this is your LR1 DFA. Now what you want to do, you are basically saying that stack contains AC at some stage of parsing. Okay, so in the stack you have AC, right? What does this mean? Can anyone tell me? If you have A and C in the stack, it means you are basically uh, at state 2, isn't it? If that is the thing, then you are in the state 2. See, there are two things. One is that how to make this DFA, which most of the students know how to make this DFA. This most of the students know, but many of the students doesn't know that how to make use of this DFA, or how to understand this DFA, or how to run this DFA, right? If stack is having AC, then first thing is to decode that what does this mean. It means basically, it means we are in state 2. Okay, this is very important information. Now, if in state 2, if next symbol is a small b, then if next symbol, okay, it could be anything, but if next symbol, immediately next symbol is a small b, then I will reduce this small c to capital B. That is what state B is saying, state 2 is saying. If next symbol is a small b, if next symbol is small b, I will reduce, right? So this is the answer. This is the answer. Is this understood to everyone? Okay, so B is the answer here. It was easy question, I think, but the main problem with this question is that many students doesn't know that what does this being in state 2 means. What does this being in state 2 means, or what does this, if stack content AC, then what does, how to infer this? Okay, stack content AC, stack contains AC, it means we are in the state 2. Okay, it means we are in the state 2. That is the most important information. Okay, let's solve this question. I think this question was the easy one. What they are saying, consider a classical dynamic philosopher problem with arbitrary number of d diners. So number of resources, sorry, number of processes are d, right? Thus, furthermore, each diner d equal to 1 to d may require different number of hd spoons. Okay, so number of resources that each one is needing. Okay, so each one is needing hd spoons. Each one is needing hd spoons, right? Uh, for example, it is possible that one of the diner is octopus who for some reason refused to begin eating before acquiring 8 spoons. Okay, so this is just for the example, which is fine. Now what they are saying, what is the smallest number of spoons needed to ensure that deadlock cannot occur? So we need to make sure that deadlock cannot occur. So how to solve these kind of questions? What we will do, we will say that okay, the number of minimum, see, if I have lot many resources, then obviously there will not be any deadlock, everyone will be having hd, and that's fine. I mean, if I just have, let's suppose, hd into d, okay, if I have at least these resources, then there will never be a deadlock. But can I have even lesser than this, and I will say okay, there won't be any deadlock? Can I have even lesser than this? That is the question, right? So basically, okay, as d depends on the d depends on the diner, which is fine. So basically, if I have s1 plus s2, okay, till sd, if I have these many resources, then that is fine. I mean, if I'm basically fulfilling everyone's request. But can I have even lesser than that? So what will I do? I will be having -1 -1 -1, right? So I will be having these many resources, right? These many resources, and I will give one more to break the deadlock, right? I mean, this is the standard problems that we do. So I will give one more to break the deadlock. So what is the answer here? So Om Dwivedi is saying, can we utilize the property in the heap that kth largest will be can lie below k minus 1 levels? Yeah, you can use those properties if you want, but it was just easy question. So that heap question was easy question, so yeah, you can directly do. Okay, so A is the answer here, right? A is the answer here. It was nice but easy question. Now let's do this question. In this question, few of the students were literally confused. So let's just do this question nicely. Okay. So what this question is saying, that you have fn plus small o of fn. Okay, where small o denotes the uh, I mean this o denotes the small o, which is fine. Now this is equal to which one? What was your answer? This is really a, I can actually say this was really a cute question. Okay, because there was a high chance of making this question wrong. Okay, if we are not very attentive. So what was your answer of this question? Okay, in the examination, I mean the real answer obviously I know. Okay, I mean we can definitely check the real answer, but what did you mark in the examination? Okay, that is what I'm asking you. Okay, so okay, all of you marked A. That's really nice. So see this. This is Fn plus small of Fn means what? Can you tell me what does this small of n square means? Can you tell me? So small of n square. So see, if I'm writing Tn equal to order of n log n. What does this mean? This is capital O. It means that Tn is actually less than equal to n log n, right? Similarly, if I'm writing, okay, if I'm writing Tn equal to, let's suppose, small of n square or n log n, let's suppose. What does this mean? It means Tn is strictly less than n log n. I mean, I'm using informal notations, but that is fine. Okay, these are some informal notations, but this is fine. Okay. So, what are the values of Tn which satisfy actually this? You have to take something which is like n log n, something like this, right? Something strictly lesser than n log n. So the values of t which satisfy this, something like this, right? Log n, something like this. So these are the values of t which are satisfying this equation. So if I say fn plus small of fn, then what are the things which satisfy this? I mean, to what quantity you can replace this? You cannot replace this with more than fn. You have to replace this quantity is strictly lesser than fn. Okay, that is the crux of this question, right? This is the crux of this question. Since this quantity is strictly lesser than fn, so finally this is fn plus something which is lesser than fn, so it is fn only, which is theta of fn, right? That is the reason this question was nice. Okay, generally we think, okay, this should be greater than fn, so maybe it will be something like this, right? But maybe it is c. Okay, maybe most of the people have done c in this question because of the overlook. Anyone here who has done c? Anyone here who has done c? Don't lie. Okay, there will be people who have done c. Great. So yeah, so Avadhut is saying that he has done with the same approach. That's really nice. Okay, now let's just do the next question. This question was again nice question, right? This question, I think, 1 mark question. This question was still a 1 mark question, but again this question was a nice question. What they are saying, you have a graph with 9 vertices, okay, that is either having 1 or 2 edge weights. Now you make a subgraph, okay, it is a subgraph. Now notice that in this subgraph you are taking all the vertices, but you are taking only few edges. Okay, so see, G is, they are saying V comma E, and G dash is V dash comma E dash. Sorry, V comma E dash. Okay, not B dash. That was the idea in this question. So they are saying this subgraph is containing all the vertices but less edges. Okay, and what is this E dash? E dash is set of all edges which are having the weight 1 in G. So basically whatever G you have, okay, whatever G you have. So from this G, you will be taking, okay, you will be taking all the weight 1 edges. I mean, you will be definitely taking all the vertices. For example, let's suppose this is 1, this is 2, this is 1. If you are making G dash from here, okay, then you are not only taking, let's suppose this is 1. You're not only taking the edges with 1, but I mean, basically you are not just saying, let's suppose this is A, this is, or maybe let's suppose this is capital A, this is capital B, this is capital C, this is capital D, capital. So see here, You are not just taking this. You are not saying A, B, C, or maybe, okay, let's just have this at the end. Let's just have only this. Okay. No, not you are not just saying this. You are not just taking A, B, and C. Okay. Is this the correct GDS? Is this the correct GDS? Tell me. Given this, is this the correct GDS? No, right? You have to take all the vertices. Okay. I mean, as you might not be taking, but yeah, you have to take all the vertices. So in the GDS, all the vertices are there. Okay. Now they are saying, okay, in this question they are saying that what is the weight of the spinning tree if this subgraph has two connected components. Okay. So this GDS, whatever GDS you are making, this GDS is having two connected components, right? Then what is the final weight of the spinning tree in this G? So see here, this G dash is basically having two connected components. One is this, okay, and one is this. Now since all of this are only edge weight 1, okay, I mean this is connected with edge weight 1. Tell me, can this have a cycle with edge weight 1? It can have the cycle, okay. I mean this is just one component. It can have the cycle, it can also have the cycle. But yeah, but that's fine. I mean I'm not worrying about it. But yeah, these are the two components, okay. These are the two components which are disconnected. But yeah, these internally these are connected. Okay, so internally these are connected, but yeah, these are two disconnected in the sense that we have to connect it. Now whenever we will find, okay, a spanning tree in G, what we will do, we will apply the Kruskal's algorithm. I mean you can do with Prims, but I'm just telling you to do the Kruskal to solve this question, okay, because it will be easy approach. Now what will Kruskal do? Kruskal will in G, okay, see, let me just tell you that what will Kruskal do in the G. So Kruskals will be keep on taking, okay, all the edge one. Whenever, let's suppose there is a cycle, okay, whenever there is a cycle, Kruskal will not take it. Okay, whenever there is a cycle, Kruskal will not take it. First it will take all edge weight 1. So if you take all edge weight 1, then you will be having one component definitely, and you will be having one component here definitely, right? So if you talk about G MST of G, okay, there will be one component, there will be one component here. Obviously it is MST, I will not be taking cycle, so it is almost same as G dash, just the difference is that I will not be taking the cycles. Okay, it is almost same as G dash. I mean it will also be having definitely two components only. Why? Because G dash is having two components, so MST of G will be having, currently if I only take one, okay, if I only take one, then it will ended up, I mean I will end up in the situation something like this. Then I will start taking two. Since there is no chance of taking two, so that's why I mean taking one, so I will be connecting these two by two, right? So that's all. So see here that one edge I have taken of 2, and since there has to be, these are 9 vertices, there has to be 8 edges, one edge of 2 and remaining 7 edge of 1. So finally 9 is the weight of MST, right? So this was really a nice question in this sense. Okay, so by the way, this question I've taken from Stanford. Okay, so this question I've taken from Stanford. This was really a nice question for this particular, AIMT, I can say. Is this understood to everyone? Let me know. Yes, I will be taking all the solutions, okay, for the previous AIMT also, but let's just first finish this. Now let's see this question. This was the easy question. They are saying which of the following is not true. Okay, so I mean may not be that much easy, but yeah, it was a good question, I can say, right? So these two you can, this at least you can do with the Venn diagram, that if A is a subset of B, then obviously probability of B will be greater than or equal to. So I think this is true basically, right? This is true. Okay, what about this? See, generally these things are not true when you are basically comparing with a different domain. Basically, it is a different sample space given B. It is a different sample space, right? It is original sample space. It is reduced sample space. It could be the case that this is completely zero. If A and B are disjoint, then this could be completely zero, right? Given B, what is the chance that A will be happening? Obviously zero, right? So 0 is greater than or equal to, and probability of A could be non-zero. So that's why this is false. See, generally these comparisons are false where you are having the reduced, I mean, you are having two different sample spaces. Okay. Now, what about this? Option C. Option C is little interesting. Probability of, they're asking A intersection B. Okay, is this true or false? Is greater than or equal to probability of A plus probability of B minus 1. Okay. So that's what they're asking. Let's just see this. So what is the relation between these two? Do you know what is the relation between these two? Maybe you can apply A union B formula first. It is basically probability of A plus probability of B minus probability of A intersection B, right? So probably you can take it here, okay, and one here. So this whole thing, okay, if you do this whole thing, if you take this one here, this will be 1 greater than or equal to probability of A plus probability of B minus probability of A intersection. Okay. So this whole thing is nothing but A union B, which is anyway some probability which is less than or equal to 1, right? So you can take this there and then you can solve this question. That was, that was one of the nice question, but yeah, easy one to be honest. But yeah, sometimes it doesn't get clicked. See, actually, whenever these two things are given, so definitely we have to apply this formula, okay? Because this formula relates these two. So that's why this is false. This is true. Okay, let's just check this. These kind of things, whenever you have the equality or something like this, probably generally most of the times you can apply Venn diagram. Okay, use the Venn diagram. So what they are saying, A is there, B is there. Okay, so A intersection B complement. So this is B complement and A intersection, which means I think they are talking about this area. Okay, so basically on the left side they are talking about, I mean, the left probability is talking about this area. Let's just see what does the right probability talk about. So left probability is talking about this area. This is saying A union B. A union B is the whole thing minus probability of B. Probability of B is this. So I think they are talking about this area. Yes, they both are talking about the same area. Right? So they both are talking about the same area. This is true. Okay. So actually this is also true. So which of the following is not true? Then B is the correct. Okay, because generally if this is a different sample space, this is a reduced sample space or reduced domain, this is original sample space, so generally these are not related. Now let's solve this question. This question was, I think, again, it was a nice question. So maybe it is easy, but it was a nice question. So what they are saying that, I mean, nice in the sense that some creative questions, right? So we are just trying to put more creative questions so that our chances, or maybe our test series questions chances increases. It will be similar to, questions in the GATE 2025 or maybe later on. Why? Because if we are putting more creative questions, then obviously there's a high chance. If you're just replicating the old questions, then probably they might repeat those questions, but it won't benefit you, right? If you're attending the test series, then it won't benefit you in terms of the creativity part. So yes, that is necessary that we should be knowing those concepts also. We should be quickly able to solve those kind of questions also, but it is also necessary to basically see that how to solve some new questions, right, which are not there earlier. So yeah, so here they are saying that which of the arrival time of t would preempt this d. So I think that was the easy question. Maybe this question was done by most of the people. So if you take t equal to 3, it will not be preempt t equal to 5, t equal to 8. So these are not the answer, and t equal to 13 was the answer here, right? So is this fine or should I do this question? Okay. So I think this is easy question, so you can do it. Yeah, this is interesting question again. So the similar kind of question we have put in AIMT one. Do you remember with these similar symbols? With these similar symbols we have put in AIMT one. Now with these similar symbols we are also putting in the AIMT two, right? I mean we have also put in the AIMT two. Now with these similar symbols, okay, we might put in AIMT3. So in AIMT1, that was a selection sort, I think, right? Selection sort question. Do you remember the selection sort question? Now it is a binary search tree. So these two are different concepts. Now there is a third question could be, do you want to guess? A different algorithm question could be asked using these symbols. Okay, we will be asking using these symbols in AIMT3. Any guesses? Any concept that we will be asking using these symbols? So we will be asking, let's not just reveal it because it will not be a fun. Okay, but we will be asking one question related to some algorithm concept in AIMT3 using the same symbols. Okay. Okay, so so someone is saying these symbols are nightmare, but it won't be. Let's just solve this question. Okay, let's just solve this question quickly. So by the way, are you aware about the in order projection? I mean, how to do in order for the binary trees? Let me just tell you, binary search tree especially. Okay, so suppose you have a binary search tree, then if you want to do in order, then you can understand this in order by the projection. Okay, that you are projecting on this line. Okay, like this. So basically in order will be D B E A F C G. So basically, I mean, obviously you have to draw the tree clearly. It should not be the case you are drawing like this. Okay, this is B, and then this is, let's suppose, C, and you cannot say that okay you are drawing like this. Okay, E is here. Okay, not like this. Okay, if you do, then obviously it will be wrong. So you draw it properly. I mean, if it is your left side, just draw it on the left side only. Okay, if you draw it properly, then in order is actually very easy. Just do the projection, and obviously it is sorted, right? In order is obviously sorted. So this is a sorted form of the, I mean, in the binary search tree it will be sorted. Yes. Yes, it will be a series of questions. Okay, so for these symbols, it will be series of questions. Now let's just solve this question. Now, first, with this, you might have guessed it that okay, what we are going to do next? We are first finding out the in order. Okay, because I mean, you can quickly check the order between the elements using the in order, right? So if you find the in order, then what will the answer? Let's just find out the in order first quickly. So you will say that this will be the first one, then this one, then this one, okay, then this one, then this one, then this one. So these are the symbols. Now probably since this is the lowest one, you can quickly assign some number here. Okay, since this is the lowest one, so maybe you can assign 3. Okay, maybe let me write some numbers here: 3, 5, 6, or maybe 1, 2, 3, 4, 5, 6. So 1, 2, 3, 5. Is this fine to everyone? I mean, if you want, you can assign numbers. So which means you can say this is 1, this is 2, this is 3, 4, this is 5, 6. This. Now they are saying okay, 7 is here. Is this fine? See, this is very important. Okay, this is very important. I mean, if you do this, this question will be just straightforward. Okay, I'm not sure if it is a 1 mark or 2 mark. I think how many marks? What was it? Uh, okay, this was a 1 mark question, right? Okay, because this is question number 35. Yes, till question number 35, yes, this is 1 mark question. So this will be 1 mark question. Okay. That's fine because this question was not too tough. Okay. So we can do this question. Now they are saying that okay, if you have 7 here, what is the place of this? Right? So again, see the 8 you cannot fill. I mean, you have to basically use all of these elements only, right? And and here we have, these are the 7 elements, but one of the element we are not using. I mean, see, these are the 7 elements. These are also the 7 elements: 1, 2, 3, 4, 5, 6, 3, 3, 6, and 7, right? So this 8 anyway we cannot use. Okay, so we are not using this 8. Yeah, we are not using this 8 at all, right? Now um let's just quickly do this, right? So this should be how much? This should be how much? See, again let me quickly, okay, let me quickly do the projection because it will be easy. and then uh, this, then this. So see, I'm asking about A. So what I'm asking basically, A should be the highest one, right? I mean after, sorry, I'm not yeah. So after the 7, A should be the highest one. Okay, so 7 can be here. So what does this say? 7 must be here. What does this say? Can you tell me? I mean in terms of number, what does this say? It should be 6, right? I mean A should be 6, and this should be 5, this should be 4, this should be 3, this should be 1, this should be 2, this should be 1, right? So this 1 is basically here, this circle will be here, this 2 which is infinity will be here, okay, this 3 which is like triangle kind of shape will be here, like this, right? You can even fill this completely. Okay, so by the way, given this binary search tree, how many ways, okay, any binary search tree, if the structure is fixed, okay, and if I just ask you, these are the distinct element using which you have to fill this structure, so how many ways, with how many ways you can fill this structure? Tell me. Let's suppose this is the structure. Okay, let me make some nice diagram. Let's suppose this is the structure. Okay, so with how many ways you can fill this tree? Tell me. Yes, only one way, right? So basically in order, see here you have to have, okay, whatever is your numbering, I'm just calling it smallest number, I'm calling 1. It could be 5, 10, anything smallest. You have to have smallest, then next, then next, then next, then next, then next, then next, right? So there is exactly one way, given this structure, there's exactly one way to fill this structure. Okay, because see here, this should be one only, smallest has to be here. There is no other way that the smallest can be anywhere at any other place. Second smallest has to be here, third smallest has to be here, fourth smallest has to be here, highest has to be here, right? Exactly one way. Although I made this question MSQ, okay, although I made this question MSQ, and I was asking uh okay, maybe complete screenshot I have not taken, but let me just take the complete screenshot. Okay, so I was asking that what could be the possible object in place of A. Okay, so see, I made it MSQ, but it was not required to be MSQ, because there is exactly one. There will be exactly one way to fill this. Okay, there are no multiple symbols can come at place of A. Although I was saying that objects, what could be possible objects, it was MSQ, but yeah, there will be just one answer. And what is that answer? B. Why? Because if you check this, that at this place 6 must be there, and 6 means this particular diagram. Okay, is this fine to everyone? Let me know. Okay, so there is exactly one way for any given diagram. Although I made this MSQ, but it was not required to be MSQ. I mean, it was just to confuse you that it was MSQ. Actually, Deepak was saying to me that why you are making this MSQ. Okay, I mean, Deepak was just I was having discussion with Deepak regarding this question, because this question was nice question. So if some questions are, some some nice questions, some different questions, so we discuss with each other. Although like let's suppose it is for my subject, still I will share it with Deepak, because it is seemingly good, and similarly Deepak does with me. So when I told Deepak about this question, then he's saying that, okay, should we make this MCQ MSQ like this? So then I said that, okay, I will be making this MSQ, because it will be more confusing to students. Okay, but yeah, this was a good question. See, if you do this, how many of you know this in order projection thing? If you do this using the projection, then you can easily solve this question. How many of you know in order projection thing? Okay, so this is the answer. This is an answer. Now let's solve the next question. Yeah, this question was tricky one. Okay, and this was 2 mark question. So let's solve this question. What they're asking in this question is that an inversion in an array of A. So they have defined the inversion. For example, they call it inversion if I is greater than j, but which means when you go along the array, okay, which means this, but AI is basically lesser than, or maybe you can define another way. If I is lesser than j, I is lesser than j, but AI is greater than aj. So AI is greater than aj, which means let's suppose I equal to 2, j equal to 5, which means this is, let's suppose 2. Okay, so at this position you are having a higher element. Okay, then it is an inversion. For example, if you are having, let's suppose, sorted array, then inversions are 0. Okay, sorted array if you have, then how many inversions you have? Then inversions are 0. Why? Because it is basically, so it is fulfilling the condition that is smaller at a small index. Okay, if there is a higher at a small index, so then we will call it inversion. Now what they are saying is that there is array of length 100. If we are exchanging A10 and A30, the maximum number of inversions, the maximum number of inversions that can be removed by exchanging A10 and A30. So that's what they are asking. Okay, so let's just solve this question. See, suppose, okay, let me make this array little. Suppose this is A10, this is A30. Okay, now whatever the inversions, let's suppose this particular number, right? Maybe this is, let's suppose, 5. Okay, but this is not in the sorted order, this is higher number, let's suppose 7, right? Is this having inversion with 5? Tell me, is this having inversion with 5? Yes, because it is basically higher number, right? It is not sorted, so it is having inversion with 5. Now suppose if I put this 5 here, okay, or anywhere else, I mean if I shift this 5, as long as I shift this 5 anywhere on the right hand side, okay, not on the left hand side, so the 7, let's suppose I am shifting it here, is 7 still having the inversion with 5? Tell me. Earlier it was having when 5 was here, it was having inversion with 5, but now the 5 is at a new place, which is the right of it, which is fine. So is this having inversion with 5? Yes, right. So basically shifting this, I mean shifting this 5 from here to here or here at anywhere place, so this doesn't matter to any, to these elements, right? If it is earlier having inversion, then also it is now having inversion. If it is not having inversion earlier, then if it was 2, then it is not having inversion with 5, then you can put 5 anywhere. So basically if you are exchanging these two, then number of inversions doesn't matter to this, to the all of these guys. Similarly, number of inversions will not matter to all of these guys. Why? Because if earlier that was the inversion, let's suppose it is not the sorted order, let's suppose it is 2, but it was the 5, right? It is 5. Okay, so yes, this is an inversion. Now if you put this 5 here, okay, then also this 2 and 5 are inverts, and then also 2 and 5 are having inversion. So basically what I'm trying to say here is that if you are basically exchanging the elements in between these two, if you're exchanging the elements in between these two, the number of inversions doesn't matter to this, number of inversions doesn't matter to this, right? I mean number of inversions won't change with respect to these things, with respect to these guys, right? So maybe they will be changed with respect to each other, maybe they will be changing with respect to each other. I mean we don't need to worry about this and this array. Okay, so let's just focus on only on this array. Now they're asking what are the maximum number of inversions that can be reduced. Okay, so see this, suppose this was some element. So let's just see this in this way. This was some element, which is having, let's suppose, inversion with all of these guys, right? Suppose this is some element which is, let's suppose, 100. Okay, so the question was that maximum number of inversions that can be removed. Okay, so for that I need to have first maximum number of inversions. So if this is 100 and these are all the smaller numbers, okay, or maybe these are the smaller numbers but in the reverse. So basically, first of all, let's just have the maximum number of inversions. So maybe you can have something like this, right? 100 and uh, then 90, then 80, 40, 30, something like this, right? I mean, with this way, this will be maximum number of inversions, because 100 will be having the inversion with all of these, 90 will be having the inversion with all of these, right? 80 will be having the inversion with all of these. So it will be maximum number of inversions in this case. Okay, now if you're exchanging 130, okay, then how many inversions you will be removing? Let's just check. So suppose now this is 100, this is 100, and this is 30. Now in this case, what will happen? Can you tell me the number of inversions? See, earlier 100 was having inversion with all of these guys, right? All of these guys. Now 100 is not having inversion with any of this, right? Similarly, 30 is not having inversion with any of this. So if these are 1, 2, 3, 4, 5, 6, 7, 8 elements, okay, currently let's not worry about this. So these are the 8 elements, suppose, then 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 this 100 was having inversion with 7 elements, 30 was having inversion with 7 elements. So 7 into 2, these inversions you are reducing, because 100 was having inversions with 7 elements. So now 100 is not having an inversion with any of this, right? 30 was having inversions with these 7 elements. Now 30 is not having an inversion with any of this. So these 14 inversions, or maybe if these are the, let's suppose, total number of elements, you can say, let's suppose, if these are the total k elements, okay, including both of these indices, then you can say 2 into k minus 1 inversions you are reducing, right? Because k minus 1 inversions for one of this, k minus 1 inversions for this, so 2 into k minus 1, I mean k minus 1 inversions you are reducing for this, k minus 1 inversions you are reducing for this, right? So you're reducing 2 into k minus 1 inversions. Are you reducing some extra inversions? See, this is also the reverse, right? I mean, 90 was having inversion with 30, right? 80 was having inversion with 30. I mean, we are done with this 100, but let's just talk about what about these k minus 2 elements. I mean, we are okay. I mean, we have considered these two elements, but what about these k minus 2 elements, right? So earlier 90 was having inversion with 30, but now 90 is not having inversion with 30, right? I mean, this is sorted. So basically, for every of this guy, I'm basically, these are the k minus 2 guys, right? So for every of these guys, I'm actually reducing one inversion. So what it will be? 2k minus 2 plus k minus 2. Sorry, I'm over counting it, because see, 130, so 100 was having inversion with all of this, so these were the k minus 1 inversions. Yes. Yes. So I have already counted it, right? I mean, I've already counted that 90 and 30 was, when I was counting for 30, I have already counted that, okay, 90, 30 inversion, right? I mean, now they are not having any inversion. So basically, I mean, okay. So 2k minus 1 will be the total number of inversions that you will be reducing, right? I mean, you will be reducing k minus 1 inversions for this. You will be reducing k minus 1 inversions because of this, right? So if k is the number of elements here, which is 30 minus what is the number of elements? Number of elements, this is, okay, a 30 minus 10, 20 plus 1, right? So 21 is the number of elements here. So 2 into 21 minus 1, which is 20, so 40. Yeah. So there is one more thing that we need to check. See, k is the 2k minus 1. Okay, there will be one thing we have over counted, right? Yeah, okay. So basically k minus 1 inversions for each, but these two are also having the inversion, right? These two, we have actually over counted one inversion. One inversion we have over counted. Okay, so maybe I can just tell you again. See what I'm saying, that if you are exchanging these two, let's suppose you're keeping the 30 here and 100 here. Now, what is happening for this, right? This is earlier, this was having these k minus 1 inversions, right? These k minus 1 inversions. This 30 was also having the k minus 1 inversions, but this 130 inversion I'm over counting, right? So k minus 1 into 2, these inversions I'm reducing, but one inversion I'm over counting, so that's why plus 1, right? Okay, so I'm not reducing that inversion, so 2k minus 1 is the total number of inversions that I can reduce at max. So which means if k value is 20, okay, if there is a 20 elements here, right, then 2k minus 1 will be 39. Okay, is this okay to everyone? Now so maybe you can understand with the example, or maybe, oh, I think the other way will be little more tough if I don't give the example. Maybe you can directly understand with the example that this 100 was earlier inverting, right, with these k minus 1 elements. Now since 100 is here, now 100 is not having inversion with any of this k minus 1 elements, right? So that's why these k minus 1 inversions I'm reducing. Okay, 30 was also having the inversion with these k minus 1, right? So but actually this I already counted, so you can directly add k minus 2 if you want. Okay, or maybe I can just double count it and then add 1. So 2k minus 2 plus 1, 2k minus 1, right? These are the inversions which we will be reducing. Okay, now let's solve the next question. Yeah, so this question was little tricky in the sense that here I was using the max operator and then we were using the negative sign. Okay, so let's just solve this question, what they are trying to say. So they are saying in a game where two players take turn picking card from either end of the sequence. Okay, both players aim to maximize their total value to play optimally. So they are saying, for example, this is the number 4913. Okay, if player 1 do greedily, if player 1 take this 4, then it is giving a chance to take 9 to the player 2. So player 1 should not directly see the 4 and take it. Okay, it should be taking 3. I mean basically ideally should be taking 3, because if it take 4 then 9 will be given to the player 2. It should not be taking 4. Okay, so greedy approach won't work here, right? So now they're asking which one is true. So there are basically, you can say there are if this is Si to Sj, there are basically I two possibilities. Player 1 takes I or player 1 doesn't take I, right? Player 1 takes from this left end, okay, takes I or takes J. Right? These are the two possibilities. Now if player 1 takes I, then the value it is adding is Vi. Here the value it will be taking is Vj. These are the small Vi and small Vj, right? Now this Vij is the maximum score the first player can achieve on the subsequence from index I to j. So basically Vij, this is the maximum score a player can achieve from I to j. Okay, given I to j. Now if you are taking Vi, now you need to make sure that the second player, whatever it will be choosing from I plus 1 to j, right? Here it will be choosing from I to j minus 1, right? So second player will be choosing this one, right? The second player will be having this value. So this value you need to make sure that this is minimized. Okay, this particular value you also want to minimize, which means you want to make sure that okay, you are choosing vi, that is fine. See, this is not a typical dynamic programming problem, because in the typical dynamic programming problem you just have one person. Okay, you just have one person who will be taking dynamically. So this is little different from the dynamic programming. Okay, this is something called, there is something called as minmax. This is little different from dynamic programming. It is minmax optimization. Okay, in the sense that you also have to make sure the remaining score is minimized. Okay, so basically you will say that this particular thing should be minimized. So if I use a maximum symbol, then you can say this vi minus, you need to put the minus sign if you're using the maximum symbol, or maybe you can choose minimum sign if you want. You can say vi plus vi plus 1 to j. I mean, whatever is the remaining one, it should be minimum. Okay, but since I also have to this is very tricky. Okay, I also have to maximize my score. So anyway, I will be, you cannot use the minimum, because anyway I have to use the maximum, because I have to maximize my score, because otherwise I cannot use the minimum, because my score itself will be minimized, right? I have to maximize my score, but at the same time the remaining value should be minimized. So that's why I'm using the minus symbol here. At the same time the remaining value should be minimized. So this is one typical problem that they may ask. Okay, this is extremely different problem from the typical dynamic programming questions. Okay, we have two players here, not just one player. If you're gate DA student, then probably it will become in the alpha beta pruning, or these kind of, in artificial intelligence, this kind of, okay, some similar, I mean, in that you will be studying something else, but yeah, similar kind of setup you might see. Okay, if you're gate DA students. So basically you have to maximize this vi and vj. That's why the maximum symbol should be there, but at the same time you have to minimize the remaining one. Okay, that's why this minus symbol is there. See, if you're maximizing fx is same as minimizing minus fx, or vice versa, which means minimizing fx is same as maximizing minus fx. So basically this is more applicable here. I mean, I want to minimize this, so I'm putting the minus and maximizing this. Okay, I'm maximizing, putting the minus, and so it is not, I mean, that's also good, but it's not required here. So you can understand like this, that minimizing something I want to minimize is just same as maximizing negative of this, right? So Vas is saying, why we count inversion? Is there any use case? Yes, inversion is useful. For example, there's an insertion sort, right? So insertion sort is one of the technique which is which can be, I mean, one of the way to understand the insertion sort is using the inversion. And there are other use cases also, that how much different. I mean, how many odd things are there? How many inversions are there? I mean, how many, you can say, how many elements which are not sorted. Okay, or maybe, I mean, it could be your use case. Maybe you are having some problem statement, you are seeing that okay, there is some sorting, but it is not 100% sorted, so how many are disturbed, right? Something like that. How many are disturbed from that? So is this understood now? See, this is not exactly fitting into the dynamic programming paradigm, in the sense that in the dynamic programming we just have one player, but we want to, in this case we are having two players, so we want to make sure that remaining score is also minimized, right? That's why I'm putting the minus and having the maximization. That's very good question. It is a typically different question from the typical algorithms, but yeah, it is a very good question. I put this question intentionally, because sometimes we should be having a different questions. Okay, see, from the last 2 years, Gate has been very kind to you. To be honest, okay, Gate has been easy from the last 2 years, but sometimes they ask, okay, they ask some different questions also. Okay, so we should be having those questions sometimes in the AIMTs or in the mock test, so that if they directly ask in gate exam, at least either you can skip that question, or you are having the mindset that okay, these kind of question can also be asked. Okay, so yeah, so basically this is the answer. Okay, I have taken this question from Stanford. Okay, now let's solve my favorite question of this particular AIMT, which is the question of this Prim's algorithm. How many of you were able to solve this question? Tell me. Tell me honestly that how many of you were able to solve this question? See, it was a nice question, and if you understand the difference or the similarity between the Prim's and Dijkstra algorithm, okay, which rarely people talk about, but we have even a one video which is of 40 minutes. Okay, for our registered students, we have 40 minutes video. Okay, telling how to implement Prims, what is the difference and similarity between Prims and Dijkstra. Once you understand these things, okay, you will be not only able to solve this question but many other questions also. Okay. Okay, now let's just solve this question. Before solving this question, I want you to understand how does the Dijkstra work. Okay, and then I will just tell you that that how does the Prims work, just like the Dijkstra. I mean, you might be knowing the Prims, but you will be seeing today the Prims with a different angle. Okay, so let's just see how does the Dijkstra work, and then we will see how the Prim can work in the same way. Okay, so you know how does the Dijkstra work, right? What are these called? What are these called? These are called priorities. I mean, we use a priority queue, so these are called priorities. Okay, these are called priorities, right? I mean, max heap priorities or priority queue priorities, or the distances. You can also call them distances, right? So actually, I've used a similar kind of word here. That's why I'm emphasizing on this. Okay, priority. Okay. So see, you will say that okay, this infinity will be anyway 4, this will be 8, okay, and then you will be finalizing this 4. You will say okay, this 4 is final, then this is 12. You will relax all the edges. This is 12, and then you will relax this edge also. This is 11 plus 4, 15, but that's fine. This is already 8. Now you will say that okay, see, this was final. I'm running Dijkstra, okay, this was final. Then this is 12, this is 8, everything else is infinity. You will pick this is final. Then this will be 9, this will be 8 plus 7, 15, right? And yeah, okay, and then you will be again picking the minimum. I think this is the minimum. Then this is 9 plus 2, which is 11. 9 plus 6, this is 15, and I think 15, 15 similar. That's fine, right? Now now you will be again taking the minimum. I think 12, 11, and infinity, infinity, 11 is the minimum. Then 11 plus 4 is 15. 11 plus 10 is 21. 11 plus 14 is 25. So you will be picking, okay, next time you will be picking 12. So 12 plus 7, 19, right? That's all. 19 and 21, you will be picking 19. 19 plus 9 is more than 21. You will not be relaxing this way. So then this is 21. So I think most probably I have done the computation correct. So this is the answer, right? This is the answer for Dijkstra. I was running the Dijkstra algorithm here. Is this okay to everyone? First tell me if the Dijkstra is okay. Okay, then how does the Dijkstra work? Now let's just see how does Prims work. Generally we don't do Prims in this way. Okay, but we should be doing, we should be knowing that how to do Prims in the same way. Actually Prims and Dijkstra are exactly same algorithm. I will tell you how. There's very beautiful connection between them. See, how does Prims work? You will say that okay, you start with A. You will be taking what? You will be taking the minimum of this cut, right? You will be saying that okay, you will be selecting this 4, and then you will say that okay, now this A and 4 are here. Then you will be taking the next cut. Then out of this 8, 11, and 8, what is the minimum? Maybe you will be picking one of this, right? You will be, let's suppose, picking one of this. Let's suppose you are picking this, right? Now you will be taking this cut. Out of 2, 4, 11, and 8, which one is the minimum? See, this is 2, 4, 11, and 8. Which one is the minimum? Then you will say 2 is the minimum. So you will be again picking this, right? And then you will say that okay, the out of 8, 7, 6, 4, and I think this was 7, right? Yeah, 7. So this is 7. Out of this, what is the minimum? I think 8, 7, 6, 4. Out of all of this, 4 is minimum, right? So since 4 is minimum, so you will be taking this 4, you will be again taking this. So okay, it was already taken, right? So you will take something like this, and then you will be again running out of 10. This all of this, I think 2 is minimum. So you will take this 2, then you will take this h, right? And then you will, out of all of this, you will take this 7. Out of all of this, you will take this 9. So I think in this way you will be taking. Is this fine to everyone or not? Is this fine? Okay, great. Now first tell me if that is fine, then only we can proceed here. Okay, okay. So this is fine, right? Now see, what we are doing here is that we are taking this graph, right? We are taking this graph, and we are basically saying that, okay, let's just, see that, okay, which one is minimum. 4 is minimum, right? So I will be taking this, right? But how to do this algorithmically? See, as a human I did it. I mean, as a human I know that, okay, this is 4, so this is minimum, I will be taking this. Then next 8, 11 and 8, so I have to find the minimum, right? Out of 8, 11 and 8, let's suppose I'm picking this 8. So I'm saying that, okay, now this is, you know these are the, this is my cut, and then out of this 2, 7, 11 and 8, now I'm saying 2 is minimum, right? So as a human I keep on adding that, I completely agree. But as an algorithm, how will you do it? That is my question. So we will be maintaining in the exactly same way. This is exact same. In fact, if I tell you the Dijkstra, I mean, we don't need to go in much of the detail, but if I tell you algorithm, Dijkstra and Prims, you can match line by line. This line is same as this line, 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 this line is same as this line. Okay, this line is also same as this line. This line only, see, if you check, this line is same, this line is same, this line is same, only in just one of the line there is only this thing is extra, only this thing. Implementation wise exact is same, Dijkstra, Prims, you will get to understand why and what is this happening. Implementation wise everything is same, only this plus thing is extra. Okay, so we will be maintaining the heap and everything, priority queue, everything. In Prims also we do everything same as Dijkstra. Just every line if you match, everything will be same. Just this plus thing is extra. Only this is extra in Dijkstra. What does this mean? What is this? Okay, we will just understand, and then you can solve those kind of questions very easily. Actually, it is very important to understand because they may ask these similar kind of questions. Okay. So anyway, what I was trying to say here is that as a human, you know that, okay, this is a cut, right? So 4 is minimum, so you will be taking like this. Then 8, out of this, let's suppose 8 is minimum, you will be taking like this, and so on, right? So but how does Prims work? Exactly in the similar way of Dijkstra. Let me just tell you quickly. Okay, this is 0, infinity, infinity. So you just relax all the edges. Okay, outgoing edges. This is 4, so you will be saying it is 4, it is 8. Okay. Now what is the minimum? So this is final. Okay, now out of 4 in 4, 8, infinity, 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 what is the minimum? I think 4 is minimum, so you will be taking the 4, right? Now interestingly, you will not be adding this 4 plus 8. Okay, I mean, whenever you are relaxing this, okay, you need to relax in the similar way, you need to relax, but instead of 4 plus 8, 12, you will just say it is 8. I mean, you will not carry forward the older weights, because we are not finding the cost from the source. Okay, it is not a cost from the source, it is a cost from b only, or it is a cost from this cut. So basically, just to keep it simple for now, that in Dijkstra it was 12 when I was relaxing, now it is just 8. Okay, you don't carry forward these weights. I mean, the addition won't happen. Okay, this addition which I was talking about, I will just explain in a minute, but this addition won't happen in the Prims. There is no addition. Okay, so there is no addition of the weights here. Okay, sorry, this was plus w, this was not plus w, so there is no addition of the weight. Okay, so that's the only difference. So basically what you will be doing, this is 8 only. If you relax it, this is 8. Okay, now let's just keep on relaxing. Okay, now if you relax, this will be 8. Okay, so this is final, this is final, this is final. Now keep take the minimum, this will be 8. This is 11, but 8 is already there, so that's fine. And then, okay, I have all relaxed both the outgoing edges. Now now take minimum of all of this, right? What is the minimum? Minimum is 8, right? So you can either pick this or this. Let's suppose I pick C. Okay, Suppose I pitch C, which means it is final now. Now you relax this. What will be the priority of this? Will it be 10 or it will be just 2? Will it be 10 or it will be just 2? Tell me. It will be, interestingly, it will be 2 only. Right? It will not be 10. Basically, I will not be carry forwarding. That's the only difference, right? It will be 2 only. Now this is 2 out of all of this. Okay, so I think, okay, sorry, I need to relax this also. This is 4. This is not 8 plus 4. This is 4 only. This is 7 only, right? Now, since I've finalized, obviously, like B is final, right? A is final, C is final. Now, out of all of this, 2, 8, okay, this is anyway infinity. Okay, 2, 8, infinity, 4, 7, infinity. Which one is minimum? So I think 2 is minimum. So I will be again finalizing I. So I will say I is now final, right? I is now final. So this is 7. So it will be 7 basically, right? This is 6. So from infinity it will be 6. So these are the only two outgoing edges. 6, 7, 4 and 7. So I think 4 is minimum. You will be taking this. Then then you will be saying that, okay, this is 2. I mean, from 6 it will be reduced to 2 because it will not be 4 plus 2. It will be just 2. Okay. And then this is 10. This is 12. This is 14, but this is anyway 7. So it will not change. And okay, these are already final. So out of 7, 2, 4, 10 and 7, which one is the minimum? I think G is minimum, right? You will pick this G and then you will say that, okay, this is final, right? And then you will relax this. This will be again 1. Interestingly, it is just 1, right? And then this is 2. Okay. So among this 1, 2, 10 and 7, I think 1 is minimum. So you will pick this. Now, okay, the 2 was already picked. Now among the 7 and 10, I think 7 is minimum. And then this will be 9. So finally it will be 9 only. Okay. Anyway, so this is your MST that you will be getting in this order. I mean, you will be picking those, you will be relaxing, and then you will be picking those kind of those edges, which is the final edge you will be relaxing, right? So is this fine? Little bit, is this understood to you guys that how the priorities are changing in the prims? Is this little bit understood? Is there anyone who is the enrolled student and who has watched this lecture? Anyone who has watched this lecture? This was the jam lecture, to be honest. Okay, how to even implement the prims. Okay, how to take the minimum and everything I told very nicely, to be honest. Is this understood? Little bit. Now let's just apply the same thing, okay, in this particular graph, and you will solve this question in just a fraction of seconds after that. Okay. See here in the prims on Dijkstra, the only difference is that we don't update with the carry forwarded weight. Okay, we don't update with the carry forwarded weight. That's the only difference. Okay, otherwise everything is same. So now let's just do this question with the same thing. Now they are saying, what is the relationship between x, y, z and these things such that I want to have this priority? See, initially what is the priority of A? It is 0 because I am starting with A. It is infinity, it is infinity, it is infinity, it is infinity, right? Initially these are the priorities. Now they are saying that what is the relationship between x, y, z such that this priority keep on changing, which means I do not finalize on C. I will be finalizing on C at the end. Okay, I want to final C. I want to, basically the thing here is that the key point here is that I want to keep on changing. Okay, priority of C, or maybe I want to finalize C at end. Okay, this is my goal. I will be keep on changing the priority of C. I mean, that's what they are saying, right? What should be the relationship? That's a very beautiful question, to be honest. Okay, so let's just solve this question now. Okay, so this is 0. So initially what will happen? This will be, see, this is anyway final, right? This will be 2, this will be 1. Is this fine to everyone? Let's just do it step by step. I will not make any hurry in this. Is this step final? See, this will be relaxed to 2, this will be relaxed to 1. Currently there is no involvement. Okay, sorry, this will be relaxed to x. Okay, assuming x is obviously a finite number, so this will be relaxed to x. Infinity is anyway worse than x, right? So this will be relaxed to x. So C priority has been changed how many times? 1 time. I mean, they are not asking it that how many times, but yeah, they can definitely ask this kind of questions also. Okay, so maybe I have got the next question for AIMT 3, that how many times C priority is changing. Okay, so okay, I can definitely ask this question, right? So now, by the way, this is a standard university question. I have not framed this question. This question, as it is question, is a standard university question. I will keep the link in the gate outflow comments. Currently, on the slides, I don't have the link, but yeah, this is standard university. Now you see here that, okay, I have relaxed these three edges, right? Is this fine to everyone? This edge, and this edge. These three edges has been relaxed. 1, x and 2, right? Now, I will take the minimum. I don't want to take this c. This x could be 0.5, but I don't want to take this c. So basically, what should be the x? X must be greater than 1, right? See, if I want to take this g, I don't want to take this c. The thing here is that I don't want to take this c. So x must be greater than 1. Right? I mean, I will be taking this g. Let's suppose g is final. Among this 1, 2 and x, I don't want x to be the minimum. That is the thing. So x must be greater than 1, right? I mean, I don't want to finalize on x. I don't want to finalize on c. So x must be greater than 1. Let's just pick this g. So g is final. Okay. Now relax all the outgoing edges. So this is 4. This is 8. So these are the only two outgoing edges here. I mean, this is the only outgoing edge to final vertex. So let's not worry about it, right? So this is 4 and this is 8. So definitely this will be 4. That's fine. Now I want the c priority should be changed. I want to change this from x to 8. This can happen only when x is greater than even 8. Is this fine to everyone? I want the c priority to be changed again and again. So I want this to be 8, right? This can happen only if x is greater than 8. Yes. Is this okay to everyone or not? Because this is very important, idea of this question. Okay. So now x must be greater than 8. Why that is the case? Because whenever I am relaxing, see here, whenever I am finalizing g, whenever I am relaxing this is very easy to relax. This is 4 anyway. Now to relax this will be 8 and I want to change the priority. So I can change only when x is greater than 8. Okay. Now I have 3 options, 2, 8 and 4, right? I have 3 options. Which one is minimum? There is no confusion about the minimum. I think B is minimum, right? B is definitely minimum. So I will pick this. I finalize A, I finalize G, I finalize B. Okay, these 3 are final, right? Now I will be basically relaxing this. This is Y. I mean, this 8, I want to change this, right? I want to change this from 8 to Y. I want it. They're saying, they're asking me to do it. Keep changing maximum number of time. How this is possible? Y must be strictly less than 8. Then only I will be changing from 8 to Y. Isn't it? I mean, Y should be better, right? Y should be lesser than 8. That is the only way I should be changing from 8 to Y. Right? So I have changed from 8 to Y. So Y must be lesser than 8. Is this fine to everyone? Right? Now, have I relaxed all the things from B? Yes, I have relaxed. Now I have two things to select, either from 4 or Y. I don't want to select C. So just tell me, what should be the relationship between 4 and Y such that I don't select C? Y must be greater than 4 such that I select this F. There is no chance of selecting this C. Right? So I select this F now. Okay. Now the final vertex is F. Right? Now I relax this edge. This is Z, this is already Y. I want to change this to Z because they are saying it to me. Okay, keep on changing maximum number of times. How this is possible? Y must be greater than Z, isn't it? Then only I will be changing, otherwise I will not be changing. Okay, so Y must be greater than Z. So basically these are the inequalities that we are getting, and then I will be finally picking this C. Right? Then I will be finally picking this C. That's a beautiful question. Ultimate question, I will say. Okay, most beautiful question of this AIMT, probably from my questions, my side of subjects. Okay, so now you can match that which option is matching. Okay, now you can easily match which option is. Okay, by is greater than 4. Yes, that is true. GC actually means 8. Okay, GC actually means 8. So X is greater than 8, which is greater than Y, and which is greater than Z. Awesome. B is also true. Right? B is also true. Y is greater than 8. No, that is false. Y has to be less than 8. X is greater than Y. Y is greater than Z. And Z is greater than 8. I don't think z is greater than 8 is any condition here. Okay, so that is false. That is not even needed. So A and B are the correct answer. Right? A and B are the correct answer. That was the awesome question. Okay, so actually I like this question too much. Let me know if that is fine to everyone. Okay, if there is any doubt, you can just let me know. So A and B are the correct answers. So basically, people say, okay, I mean, if you check any typical coaching, okay, they will say that Prims and Dijkstra is same. I can bet you that in the obviously in the the course lectures, in the paid lectures, we have this particular lecture actually. Okay, where there's a 40-minute lecture. All these screenshots, this screenshot, for example, this is a screenshot of that lecture. Okay, a screenshot of that paid lecture. So people generally will tell you that okay, Prims and Dijkstra are same. There is literally anyone who will tell you that why they are same. Okay, so this kind of run of Prims, okay, the way I was running here, this kind of run of Prims is missing at every place. Okay, they will not tell you that this run is possible. Okay, option A, do not ensure that C changes maximum number of times. No, if that is changing maximum number of times, see, y is greater than 4 must be there, right? We have already solved this. Y is greater than 4 must be there. If C is changing maximum number of times, then y must be greater than 4, right? I mean, all of this has to be true. Okay, so y must be greater than 4. Because I don't want to, I think that was the, this is 4. Yeah, I don't want to select between C and F. I don't want to select this C, so y must be greater than 4, right? I think at that particular note we have to have this. Okay, among the C and F, I don't want to, this was y, this was 4, I don't want to select this y, so y must be greater than 4, right? And then the priority is again changing from y to z, because if I don't select this, then we have one more chance of changing the priority. Okay, we have one more chance of changing the priority. Is this understood to everyone? Let me know. Okay, let's just read this question again. What should be the relationship between x, y, and z such that we include C in minimum spanning tree as a last vertex? Okay, so we want to include in the last vertex, and the priority of C should change as maximum number of times, right? So if that should happen, then these should be, these all of this should be satisfied. Okay, that is the question. Okay, all of this should be satisfied. What should be the relationship between x, y, z such that we include C in the maximum number of times? Yes, so this should be the relationship. Okay, yes, just alone y greater than 4 or alone y less than 8, this might not, okay, obviously this might not infer that okay, this will happen. All of this, okay, maybe I can say collectively, yeah, I can say collectively, but this is inferred from this question. Okay, that that what should be the relationship. Basically, I'm breaking down the relationship between this was the MSQ, and I'm breaking down the relationship between the multiple options. So obviously it is inferred. Maybe if you want, I can put the collectively word here, but that's fine. I mean, but I think in the gate also we cannot challenge it. They are not saying stand alone which of the option is sufficient. They are not saying something like this, right? See, they are not saying your thing also. You are saying is this option is sufficiently I mean alone sufficient. I mean this stand alone is sufficient. So they are not even saying that also, right? They are saying that what should be the relationship such that last vertex, it is the last vertex, and the priority is just changing the maximum number of times, right? So all of this relationship should be satisfied. Okay, no, that is inferred in this question, that collectively, obviously matlab I am breaking the relationship between x, y, and z. to in the different options. Okay, they are not even, they're neither saying that okay standalone is sufficient, right? They're not even saying that. Okay, by the way, from this question the learning is more important, but yes, they are not even saying that standalone is sufficient. Then that is my argument. Okay, so by the way, have you understood this? Have you understood this kind of thing? Okay, this run, have you understood this run? And then running this prims in the way of trajectory. Let me know. Okay, Atharva is saying my eye has I have opened. Yes, actually this was very nice question, to be honest. Okay, so let's do one thing. Maybe there are few more questions. We can do all of these remaining questions. Maybe from the question number 50. So I think already 2 hours are there. So let's have 2 more hour of session. Okay, we can start from this question number 50, and then we can do the remaining questions in the next session. Okay. So thank you everyone for watching this lecture. Now we will be doing the remaining questions in the next session. Remaining questions are also nice. Specifically, I think this TCP question, right? Specifically, let me just see that question. So the CN, that was I think MSQ question, right? The TCP question. Yes, that was a beautiful question. Okay, so we will be solving this question very nicely. So all of these questions we will be solving. Specifically, this question. This question is also very nice question. And also I think this question is also nice. I mean, in this AIMT, for my subject I put actually little challenging question, right? Okay, so thank you everyone. Let's just meet in the next lecture. Thank you so much. Take care.